Grade 12 Physics, Fields Note number 2, Electric Potential Difference. This is a note that's going to look at electric potential energy in an electric field. This is something that we sort of saw in grade 11, especially when we talk about potential difference. Potential difference is just a fancy name for voltage. Let's compare it with what we know, and what we know is what potential energy looks like in a gravitational field. So let's draw here a ramp with a ball on top of it. We know that at the top of the ramp, the ball has a lot of gravitational potential energy. And when it gets to the bottom, it has not a lot, so it has low gravitational potential energy. This is just something that we're used to, something we've looked at before. But a way I want you to look at this time is that objects in nature always have a tendency to move to a position or a state of low potential energy. So if an object has a lot of potential energy, it will always want to move to a spot of low potential energy. Therefore here the ball will want to roll down the ramp, because at the bottom of the ramp, that's a spot of low gravitational potential energy. We can also look at a spring. If you compress a spring, you're giving it potential energy. But when you release it, it wants to go back to that regular length because that would be a position of low potential energy. In this unit, a charged particle, which is at a spot of high potential, will always want to move to a spot of low potential. So let's take a look at what that looks like. So let's look at potential energy here in an electric field. If we have some charged object, let's say we have some large positively charged object, and there's a negative, let's say an electron, at some height above that positive charged object. We know they want to attract each other, so really because it's raised to that height, it's sort of given a gravitational potential energy. But here, it's an electric potential energy because the attraction is due to the electric field. That electric potential energy comes from the equation E equals QV. So this is something we saw in grade 11 where voltage was energy per charge in a circuit. So rearranging that, we get this potential energy is equal to charge multiplied by voltage. So V is the potential difference in volts, E is the electric potential energy in joules, and Q is the charge of that object in coulombs. If we look at the units here, the left side is in volts, the right side is in joules per coulomb, but here we have to remember that a volt is defined as a joule per coulomb. So left side does equal right side. Now there could be a time in the unit here where maybe instead of raising an electron above a positively charged object, we might just want to find the potential difference at any point in space above some sort of a charged object. So what is that potential difference? How can we calculate that? We can do a short derivation here to make a formula to find the potential difference at any space above a charged object. So there's our charged object, and the mark X there will be some point in space. Using our equation here where voltage is E over Q, and remember that energy in an electric field is KQQ over R. We do a simplification, and now we can calculate the voltage at any point. Voltage equals K, Coulomb's constant, divided times charge divided by R. And that would be the separation between the two, the point and the object. We can only use this equation for a point in space from a charged object. So we're dealing with one object and some chosen point in space. Only one object, no second object involved. So again, coming back to that central idea that objects always want to move to a position of low potential, we're going to actually do a question here involving that concept. So we know when a ball is rolling down a ramp, it's going to turn that potential energy into kinetic energy, right? It turns that gravitational potential at the top, it rolls down and it converts it to kinetic energy. The same thing here will happen to a charged particle in an electric field. Let's say a proton is placed at a spot of high potential, and that potential will be 450 volts. Naturally, it's going to want to move to a spot of low potential. Here we're going to try and calculate how fast will it be moving when it gets to that spot. So this is basically just an energy conservation question. The charge on a proton, 1.6 times 10 to the negative 19 coulombs, and the mass of that proton is 1.67 times 10 to the negative 27 kilograms. So it's not rolling down a hill, but it will be between two charged plates, where on the left of those plates will be the area of high potential, and the right of those plates will be the area of low potential. So at the high potential, all the energy is electric potential energy, so QV, where the charge was given and the voltage is 450. It's going to move to the spot of low potential, where all that energy will turn into kinetic energy. Here we're just going to list the mass, and we're going to calculate the velocity. Let's not get confused here. Capital V is voltage, and small v will be velocity. So it's just an energy conservation question. Electric potential energy is being converted into kinetic. We rearrange for the velocity, and we put our numbers in. We're going to find that the velocity of that proton will be 2.94 times 10 to the 5 meters per second.